According to the Guardian newspaper, the new generation of improved climate models are showing that climate change is going to be worse than we thought. Is it true? What's the difference between the new models and the old models anyway? And why does it matter? Well, let's discuss. My name is Mallen Baker. This is the Mallen Baker Show for change makers. This video is going to be a first for me. Out of all of the ones I've done on the subject of climate change, this is going to be the first one I've done specifically on the subject of climate computer models. Climate models are the simulations that create the predictions we see so often in the press. If we get this level of emissions, then we'll probably see this much warming with these other various side effects. Here's how the Guardian newspaper reported it recently. Worst case global heating scenarios may need to be revised upwards in the light of a better understanding of the role of clouds, scientists have said. Recent modelling data suggests the climate is considerably more sensitive to carbon emissions than previously believed, and experts said the projections had the potential to be incredibly alarming, though they stressed further research will be needed to validate the new numbers. Modelling results from more than 20 institutions are being compiled for the sixth assessment by the United Nations Intergovernmental Panel on Climate Change, which is due to be released next year. Compared with the last assessment in 2014, 25% of them show a sharp upward shift from 3 degrees centigrade to 5 centigrade. In climate sensitivity, the amount of warming projected from a doubling of atmospheric carbon dioxide from the pre-industrial level of 280 parts per million. This has shocked many veteran observers because assumptions about climate sensitivity have been relatively unchanged since the 1980s. Now, if you're a young person reading that, you're probably highly alarmed. You've already been told by groups like Extinction Rebellion and indeed by Greta Thunberg that what's going on is completely catastrophic. And now they're saying it's even worse than we thought. Well, this is The Guardian doing what The Guardian does. It's taken a range of models, cherry-picked for one with the most pessimistic outlook, and then presented it as scientists say this might happen story. They then claim that experts are shocked, but they only quote the ones who are always quoted when you're doing stories about how bad it might be. So let's unpick this. First of all, let's quickly review what these models are and what they do. A global climate model aims to generate as complete a simulation of the Earth's climate as possible. The clue's in the name. These include things like how incoming solar radiation warms the Earth and the different layers of the atmosphere, how conditions will affect humidity, the circulation of the oceans plus salinity and acidity, estimates of rainfall, snow cover and glaciers, wind speed, strength and direction, how much heat is captured by greenhouse gases, how much solar radiation is reflected by snow and clouds, and so on. A typical full global climate model can be made up of 1 million lines of code. Hundreds of scientists are involved in collaborating on each one. They take years to build and to improve and are so complicated they need the power of a supercomputer the size of a small house to run. Why so much? Because they're attempting to model a huge complex system. And even then, they only get to do so at a relatively rough level. So certain factors, such as cloud formation and behaviour, happen at such a micro and complex level, they have to be broadly approximated. I mean, consider clouds for a moment. They cover around 2/3 of the Earth's surface at any one time. They can form and disappear within minutes. Depending on certain factors, they can both cool the planet by reflecting solar radiation back out to space, but they can also warm the planet by reflecting long-wave radiation from the Earth back down again, which is why clear nights are colder than cloudy nights. And of course, although we can discover all sorts of things about periods in the past, we have no record whatsoever of what clouds were like in the past. So there's no way of being sure how they may or may not have changed. So that's a key limitation. But even so, don't underestimate the upside. If you want to know the power of how such models help you to understand what's going on, here's a great example I came across when I was reading James Gleick's book on chaos theory. In the early 1980s, people were utterly puzzled by the discovery by the Voyager space probe that the red spot of Jupiter seemed to be a dynamic hurricane-like phenomenon, when of course any earthly hurricanes are relatively short-lived. They couldn't understand what kept it going and what kept it in place. Philip Marcus, a young astronomer and mathematician, decided to try to model what was known about the circumstances on Jupiter. He programmed a computer with a system of fluid equations. He wrote rules for a mass of dense hydrogen and helium. Jupiter spins fast, each day lasting 10 Earth hours, and that spin creates strong sidelong forces. So he programmed all of that in, ran the model, and lo and behold, the spot appeared. A self-organising consequence of the conditions, a stable component of the chaos of a fluid system. Now, did that model, with the very generally represented rules derived from what we knew of Jupiter from halfway across the solar system, did that represent a wholly accurate, detailed picture of the conditions on Jupiter? Obviously not. If that had been the criteria for success, then of course the model was wrong. But for the purpose at hand, the model was right enough to be useful. Which is the phrase I've used often on here before: all models are wrong, some models are useful. And that's something to bear in mind when we're looking at climate models that are being used to study climate change. They're used to give answers to all sorts of questions, some of which they're better at answering than others. The thing they can't do, of course, is tell the future. And that's because of two things. One is the complexity of the system and the difficulty for computer models to be able to anticipate particularly potential tipping points, examples where changes might be non-linear in nature. But the other, and more obviously and importantly, is that what happens in the future relating to human-caused climate change depends on the level of emissions our society produces in the coming decades. Which is why the UN advisory body, the IPCC, has promoted 4 specific scenarios based on different levels of emission levels, so that the models could give some information about the likely impacts that would come with those different levels. These scenarios are called the Representative Concentration Pathways, RCPs, because these people love their acronyms. We have RCP 2.6 at the lower end of the emission spectrum, and more controversially RCP 8.5 at the upper end. Controversial because it's based on a significant and highly unlikely increase in emissions, and it's often been mislabelled by journalists and campaigners as business as usual. And with its next report, there will be 4 new scenarios to fill in the gaps between the 4 already in use. Obviously, with lots of different groups running different models, you need some degree of coordination to get them producing results in a way that can be compared. Otherwise, you might just end up with a lot of noise. And it is worth doing. The interesting thing about the models is that although none of the individual models show a high degree of predictive accuracy, when you aggregate them all together, the average outcomes actually track current temperature rises pretty well. That's where the Coupled Model Intercomparison Product, CMIP, comes in. It was launched in 1995 by the World Meteorological Organization. It's been through several generations, with each stage becoming more sophisticated. So it's the CMIP 6th generation of models and research that's on the horizon, and which will feed into the IPCC report next year. There are around 100 distinct climate models being produced by around 50 modelling groups, although some will probably miss the deadline for inclusion in next year's report, even though the deadlines for that have been extended because of the coronavirus. These are huge projects and they take a lot of time to run. But still, so far, around 40 of them have produced results. And one thing's already apparent, which is what led to that Guardian article, which is that a number of the new models have higher climate sensitivity than the previous generation, suggesting that they expect warmer outcomes from each of the scenarios than was previously thought, by between around 0.4 degrees centigrade to 0.9 degrees. Climate sensitivity, as mentioned in the Guardian quote at the start, is the amount of warming that you'd expect from a doubling of CO2 in the atmosphere from pre-industrial levels. The important version is ECS, Equilibrium Climate Sensitivity. You can play acronym bingo with all this stuff, which is the final impact that remains after all of the Earth systems have had time to adjust to the changes in CO2 concentrations. When people say that a certain amount of warming is already baked into the system and that temperatures won't immediately stabilise if we reduced emissions right now, it's because of a time lag in the full effects of changes being realised as oceans absorb heat and glaciers melt and so on and so on. The previous generation of computer models estimated a climate sensitivity within the range of 1.5 to 4.5 degrees centigrade, which is a pretty big range, with many favouring a level around the midpoint of 3 degrees. Now, around a third of the new models that have reported have suggested an ECS higher than the upper end of that previous range. A quarter of the models have higher sensitivity than any of those in the previous generation. So that sounds quite worrying. I mean, that sounds like that Guardian article is exactly right in its headline. Well, not so fast. Firstly, note that it remains a minority of the models that are at the high end. You can, of course, play the game, but if you're promoting a viewpoint of assuming that the models grouped around the end that supports your case, well, those must be the more accurate ones. It's a perfectly natural human tendency not to be mistaken for science. And secondly, yes, work has gone into making the new generation of models more realistic by factoring in more of the aspects of the observable environment, and particularly in this case relating to that tricky cloud cover. But it doesn't automatically follow that the models are, as a consequence, giving more accurate estimates of climate sensitivity. A number of climate scientists have pointed out that those high-end values are not consistent with other lines of evidence, such as the records of past climate through history. Models are powerful and they give useful information, but they should only be taken as one source of evidence amongst others, and that's generally what scientists do. And the highly suggestive fact is that the models that give the highest climate sensitivity results actually do the worst job of hindcasting. Hindcasting is where you seek to verify a model by running it against the known conditions of relatively recent history to see how it matches recorded temperatures and other outcomes. If a model does a poor job of matching known history, then the implication is it's definitely not a reliable predictor of the future. The new models don't show early 20th century warming that took place between 1900 and 1940, and they do show warming from 1970 to 2019 about 20% faster than what actually happened. And then you might ask, with all these models, why are they so different from each other? There are a number of variables where the model makers have to make a judgment call on how to deal with uncertainty. Certain variables, like cloud behaviour, that can't be precisely modelled, so have to be estimated. The reflectivity of sea ice, what's called albedo, is one such parameter. We don't know the exact value of ice albedo. We know the range of likely measures, so different models try out different values, trying to get as close to the best estimates from measurements. And so you get modelers trying to fine-tune or calibrate their models around these different variables where we have some idea of values but not a precise idea. The temptation is to tweak the variables until you get a result that matches history. But unless you're incredibly lucky to do that by tweaking exactly the right variables, what you would do would be to match history but not to achieve reliable future prediction. So to explain the principle, if variables A, B and C are all unknown, and I assume variable A is mostly responsible, and I tweak that until my model matches history. But you know, life, it turns out that variable B is actually the important one. I match history, makes my model look good right now today, but that won't continue when it fails to match the variation in variable B, which is actually going to drive changes in behaviour. So generally, model makers don't do that. Dr. Gavin Schmidt of the NASA Goddard Institute for Space Studies said this: global mean trends are monitored for sanity, but not generally precisely tuned for. There's a lot of discussion on this point in the community, but everyone is clear this needs to be made more transparent. That's a valid approach, but it's not necessarily well understood by policymakers and other interested parties, nor indeed, it seems, by Guardian journalists. The Guardian newspaper, for its story, selected just one of those models, and it happened to be one of the two most extreme, which you would have to describe as cherry picking. Indeed, the website Climate Feedback, which gives scientists feedback on contentious climate-related content, did a page on this very article. On that site, Richard Betts from the UK Met Office said this: the latest research would be more accurately characterised as still not yet ruling out high climate sensitivity that was previously thought possible but relatively unlikely, rather than suggesting that high climate sensitivity is now more likely than previously believed. Now, as you can imagine, this sort of outcome is a gift to those on the climate skeptic side who simply dismiss all climate models as irremediably broken. And that's fine, but it's a political position, not a scientific argument. It's not the purpose of any of these models to become the single perfect expression of every aspect of the climate, so that it becomes a 100% accurate prediction machine. I mean, that would be lovely, but it's impossible, or certainly on existing computing power, and almost certainly at all. But just like the simple Jupyter model, there's lots of useful answers to a huge range of questions that are provided by models. The conspiracy theorists will simply dismiss them out of hand. The smarter skeptics, however, do have a much stronger case in kicking back against the reluctance of climate scientists to be frank about the limitations of the models, not to mention the tendency of journalists and others to create extreme scenarios to scare children with. And this criticism was acknowledged in a recent opinion paper by Professor Tim Palmer and Bjorn Stevens, which is worth reading in its entirety, link in the description below. In our view, the political situation whereby some influential people and institutions misrepresent doubt about anything to insinuate doubt about everything certainly contributes to a reluctance to be too openly critical of our models. Unfortunately, circling the wagons leads to false impressions about the source of our confidence and about our ability to meet the scientific challenges posed by a world that we know is warming globally. And this, of course, is right. Any situation where a community comes under constant attack, as the climate science community has been, the stress of that situation leads to people to change how they behave. And that can create a downward spiral when it comes to accountability and the frankness in the spirit of scientific inquiry. They then go to point out the value of the models to date. Comprehensive climate models have been effective and essential to address the concern that such a basic understanding could be overly simplistic, i.e. missing something important, such as the existence of a mode of internal variability, which could, if it were to exist, explain trends in global mean temperature. The enterprise of making models more and more comprehensive through the incorporation of computationally expensive but poorly understood additional processes has not so much sharpened our ability to anticipate climate change as left the blurry picture established by physical reasoning and much simpler models intact. And that's an important point. The more powerful, comprehensive models aren't providing us with perfect predictions, but equally, the better we model the various different factors, nothing's emerging to cast doubt on our basic understanding of the processes we see and, from the scientific theory, we expect to be taking place. Then they go on to pose what I think is a powerful challenge to climate scientists. Unfortunately, many in the community, notably those in charge of science funding, have no idea how significant and widespread these inadequacies are. This has arisen in part because of a justified desire to communicate with as much clarity as possible the aspects of our science that are well settled. While we are certainly not claiming that model inadequacies cast doubt on these well-settled issues, we are claiming that by de-emphasising what our models fail to do, we inadvertently contribute to complacency with the state of modelling. This leaves the scientific consensus on climate change vulnerable to specious arguments that prey on obvious model deficiencies, gives rise to the impression that defending the fidelity of our most comprehensive models is akin to defending the fidelity of the science, and most importantly, fails to communicate the need and importance of doing better. And then this challenge, most powerfully of all. Whereas present day climate models were fit for the purpose for which they were initially developed, which was to test the basic tenets of our understanding of global climate change, they are inadequate for addressing the needs of society struggling to anticipate the impact of pending changes to weather and climate. So where does this leave us? First, it seems highly likely that over the coming months, we will see more stories taking the new models out of context in the cause of promoting an agenda. Probably from both extremes. And that's just one of those things. Such results are fair game for the trench warfare warriors. More interestingly, I wonder if we're approaching something of a crisis point with how such models are developed. Very much in the spirit of that last critique. If so, it'll be a real test for the integrity of the climate science community, how well it responds to that challenge. Will scientists simply circle the wagons and defend the models at all costs? Or will they embrace the harder questions about the challenge of taking this to the next level? There are a number of areas where the track record of experts advising policy has taken something of a battering in recent months. And this is one of the areas under the highest scrutiny. It's going to be in a very delicate place over the coming year. And if things are handled badly over this coming period, I'm guessing that the consequences are going to be with us for a very long time to come.